In this video tutorial, I want to show you how to use the Catia V5's embedded FEA program, which is the Alfini program, to solve a transient dynamics case, which is modeled with beam elements. The supports are assumed to be simply simple support. So here's the situation. We have a simply supported beam, and there is a harmonic load applied at the distance A from the left end. And what we like to do is to, because of the elastic nature of the problem, or let's put it this way, because of the linearity of the problem, it can be done with transient dynamics features in the Catia program, and that's pretty much the only thing that's available to you because you can't do direct time integration, and therefore the problem has to be linear. Now, uh, I'm going to do this problem, at least in this video tutorial, with beam elements. Then, time permitting, I'm going to come and repeat this thing with solid elements. However, there's something that I should tell you, and that is uh, when I try to basically do the transient dynamics case, my computer crashes. So, and this laptop is the one that has better acoustics than the other one. So what I'm going to do is I'm going to do most of the stuff up to the point where I try to do the transient dynamics on this laptop. And then I will show you that when I try to proceed from that point on, my computer crashes, and I will move on to another laptop starting from exact same point and record the rest of the tutorial. Now, unfortunately, the acoustics on that other laptop is not very good, so we just have to be patient. Okay, so here's the situation. Let's go here, and I'm going to create several points here, three points which describe the geometry and a point which describes the orientation point for the beam. So click on it. This is point 0, 0, 0. Another one, 20 inches down the y-axis. So that's the other end, the other support is right here. And then because I'm applying a load at quarter of that distance, I'm going to create another point here, which is distance 5. That's where the load is going to be applied. And I need an orientation point. So for orientation point, it cannot be on that line because the cross section is 1 by 1 square. Okay, so I'll make x of 5 and y of 0. Notice that there's going to be a point here that's going to be created. This is going to be used as the orientation point. By the way, the exact solution to this problem is given by that expression. There is a caveat that I will mention to you later on because linear dynamics, transient linear dynamics that we're going to be using in Catia does not take into account initial condition. Assume that initial conditions are all 0. So with that caveat, we can compare it with this solution, which is also plotted here at the mid location. So I'm monitoring the displacement at this middle position, the mid position of the beam. Okay, middle position, and the load is applied as a quarter of the distance from the left hand point. Okay, so let's do the line. The line goes from here to here. Okay, and we're going to make it out of steel. So let's apply material on it. Metal, steel on that part. Now, if you check the default material properties that are provided to you, you'll see that it actually matches these. These actually are the row and E. I took it from the database, the CATIA database. Okay, good. Now we're done here, so we're going to go to, now, the thing is that when I mesh, uh, I cannot pick nodes and apply load on it. However, if you go to the advanced meshing tool, you can make sure that this point that's created is actually uh, one of the nodal points. Okay, without doing this, there's no guarantee. In other words, if you go to to generative structure analysis and then apply load here, it will not realize that it's actually being applied to the node associated with that location. Okay, so this is why I will go first. Let's go to generative structure analysis first. No problem. Good. And we have to do a static analysis first, because if you're going to do if you're going to do transient dynamics, you must have a static analysis first. Otherwise, your load will be dim. The load toolbar will be dim. So say fine. Now I have to mesh it. The problem is that when I mesh it, notice that I can go mesh this. However, there is no option which allows you to make sure that this point is belonging to that mesh. So cancel that. You go to advanced meshing tool. Here, the beam, if you look at the beam element, notice that there is these things that you did not have it in the generative structure analysis. So we're going to select this. Let's make it 1 inch. So there's going to be 20 elements along that line. And you click on this icon. See that icon? It says add isolated point. So this point that I created is going to get added to the nodes of this beam. Okay. There is a tolerance here for us because the node is sitting on that line. It doesn't matter. So we just say fine. Okay. So we did it. Say okay. Good. Now we go back to generative structure analysis. That's where we apply the load and restraints and all these things. So first of all, let's apply the cross-sectional property here. There's the 1D property. You click on this. It says that we have a rectangular beam. You click on the wrench 1 inch by 1 inch. That's exactly the stuff that we had here. Area is 1, so 1 inch by 1 inch. Okay, good. And you need an orientation point to close this, because you can't even close it. You click on the orientation point, you select this point. When you select it, it rotates this a little bit so that basically it aligns in the orientation that I want. Now remember, if this was a circular cross section, it really doesn't matter. You can use whatever you want. Okay. Actually, you can close it. If it's circular cross section, you can just close it, give it the diameter or the radius of the cross section, and just close it. Very good. So this is all done. You can see that. You can see here's the 1 by 1 properly oriented. Yeah. So let me hide these. First of all, these endpoints, hide and hide. And we're going to apply the first restraint here. So coincidence, sorry, user-defined restraint at that point. Now this is a pin, so I'm going to make all 3 degrees of freedom translation equal to 0. This can rotate about the x-axis, so I'll leave that open, but take the rotation about y and z away. Right. You say okay. Now this other end is a roller, so you click on this. Let me uncheck all of these so that we know exactly what we're doing. So this point, I'm going to say it does not move in direction Z, direction 3. It does not come out of the plane, direction 1. It can move along direction 2, which is the Y. That's why it's a roller. And for rotation about X is free, but the other 2 rotations, I'm just going to check it because they don't happen. Now, because of what I've done, this can go actually out of plane. You know, it can go out of plane. So what I'm going to do is to make sure that it doesn't go out of plane, I'm going to say, okay, so let's user define again. So this entire edge, we will not let it go out of the YZ plane. In other words, it cannot move in the direction X. This will actually take away all the frequencies that later on, frequencies that are associated with out of plane vibration. Now, for us right now, we're doing a static case, so those are not an issue. Now, over here, I'm going to apply a force minus 100. Now, when I put it on that point, you can see that it puts it on the point, but it knows, because of what we did, it knows that we are actually putting on the node that is associated with this point. Remember, we added this isolated point by going to the advanced meshing tool, and the value is minus 100 pounds downward, of course. All right, good. So this is a static problem. If you run it, it's just going to bend, nothing exciting. So let's actually try it. It's a static problem. It will bend, assuming I didn't forget anything. Yeah, if you look at the deflection, there we are. And let me do the average ISO and look at it from the front view because I want to show you something. Notice that material shading. Yeah. Notice that because the load is not exactly halfway in the middle, it actually not symmetric. Okay, that's because the load is here. It's not in the middle. If it was in the middle, then it would be symmetric. Anyway, so that takes care of this. We're pretty much done here. So let me deactivate this. Deactivate this plot. Good. Now, we have to exact frequency. If you're going to do transient dynamics, that means linear dynamics, modal superposition, you need to extract the frequencies first. So we're going to go insert frequency case, okay? And we're going to use the restraints that are already there. So we're going to say for reference, we're going to select the restraint that were already created right there. See, I selected this reference and I then went and selected the restraints from the static case. That's pretty much it. If I run it, I will. Oh, how many frequencies did I ask for? Let me see now. Yep. Let me see for a second here. Just a second. 10 frequencies. Okay. Some of these will be actually axial, which we don't need, but that's fine. So let's go ahead and run this thing. Let's say all. There's no reason to run the first static case, but I said all. Good. So if you look at the deflection, and under occurrences, you see that you get 10 frequencies that are extracted. Now, some of these are not actually bending frequency. The first one is, the second one is, the third one is, fourth one is not. It's an axial. So I'm just going to use these first three modes here. I mean, even if I use the fourth one, and which is axial, it's not going to contribute to the problem because you're loading this thing in the vertical direction. The other thing is that this series that I've done here, this plot, actually I use the first three modes right there. By the way, if you write omega and omega of 1, omega of 2, omega of 3, it will give you those frequencies, the first three frequencies that we have in the table. Of course, it's going to be radians per second. You have to convert it into hertz. That's fine. So fine, this is done. Now we're going to go to insert down here, transient dynamic response. Okay, you click on it. Now it says, okay, what is the reference? The reference solution frequency is the one that we just did. It requires that. See that? It does require. Okay, and it's a load excitation, and we say okay. Now notice that these loads are dimmed. Okay, these loads are dimmed. So let me do the following. Let me delete this. Do it again. So insert frequency case, sorry, transient dynamic response case. You select the frequency, and for reference, you click on the reference. You're going to select the uh, actually. Uh, no, never mind. That sorry. Let me never mind. Undo. Okay. So this comes in. Okay. Now, if you double click on this line, oops. If you double click on this line, it says. Just a second. If you double click on this, it says how many frequencies. If you double click on this frequency case, basically took that and put it in there. Do I want all 10 modes? The answer is no, I just want 3 of them. Okay, we say okay. The first three modes, bending modes. Now, the other thing is that if you double click on this load excitation, it says, okay, what is the load? The load is the one that we had from the static case. Yeah, remember we did the static case? Because otherwise, you just, you yeah, you just select that. There's no otherwise. There is no otherwise, so I just selected it. And now it says, okay, what is the selected modulation? Now, I don't have a modulation. What does that mean? Remember, this sine curve, this load that I'm applying is a sine curve, okay? Okay, it's a sine curve. Now, I have to go and use the Excel file to bring that sine curve, that's called modulation, to bring that sine curve into the problem. So the first thing I do, I put this thing on the side here, or let me start an Excel file. Oops, sorry. Let me start an Excel file. And you go here, you say, okay, do a new one. First column is uh, uh, remember the load is F naught. What is that? Yeah, F naught sine omega t. Now F naught was already applied as minus 100 in the static case. It is this curve, sine of omega t, sine of 7 pi t, because omega is 7 pi. It is this curve that I had to read it as an Excel file. Okay, so we go here. So basically, I'm trying to input sine 7 pi t in Excel in the Excel sheet. First column is x. That is the time, really. That is the time, and this is y without any units. So I just put open parentheses, close parentheses, 0, 0.01, okay? And I'm going to make, this is time. I go all the way to time of 1, which means I have to go to 102 probably, right there. Yep, yep. Now over here is equal to, remember, it's the sine of 7 times pi, which is 3.1415 times that column. Okay, and if you do this, you bring this thing down all the way. This is going to replicate those, and that's going to be sine of 7 pi t. This is going to be sine of 7 pi t. This is going to be a t-axis. This is going to be sine of 7 pi t. Now I'm going to save this thing. File, save as. I have a folder here. April 3rd. Okay, so I'll call it modulation, sine modulation, sine modulation. So I have an Excel spreadsheet which describes basically my loading. Good. Okay, you can close this. Now, back to Catia. If you look at there's a toolbar here which says modulation. This is white noise. White noise means it's a constant value basically, but I don't have a constant value. There is the frequency. You can input the frequency, or you can input time modulation. It's time modulation. You click on it. It says, okay, where is it? So browse. I go to that folder. Remember sine modulation I created? I say okay. So it now creates a, basically I'm importing a modulation. If you go here in the tree, you see that there is this thing that I imported right there. That's the Excel spreadsheet that I imported. Now, when I double click on the loading, it says, okay, where is the selected load? The selected load is right here. That's why I had to do a static case, because otherwise load, you cannot put it in there for sure. Okay. And then modulation, you go all the way to the top. You select that. You can also scale things here. In other words, if I had not applied, for example, 100 pounds downward, I could have put 100 over here, but I'm not going to do that. That's pretty much it. So let me actually save this thing. Stop April there. Analysis, I'll call it new. Say yes, that's fine. Okay, good. You're almost done. The problem, there's nothing to, you don't run anything. Already all the information that you want in there. And what is the information? You have your load, you have your modulation, you have the frequencies. It's all there. The only problem is that you put the, when I put the cursor here on the slide, see that? On the slide, okay? Right click, generate 2D display. You'll see that after a couple of steps, it's gonna bomb out. But let me show you something else that I forgot to do. If you click on the transient dynamics here, okay, it says what time frame do you have in mind? I want to go from 0 to 1 second, and the reason I want to do that is that this plot is also from 0 to 1 second. Okay, and let's make it 100 steps. This is not time integration, remember. And we say okay. Excuse me. Now, the next step is to go to this line, right click, generate to the display. No problem. So I say okay. You say next. One graph is what I want. When I say finish here, Catia, Catia will crash on this computer. So basically the rest of the problem, I cannot do it for you on this computer. I have to go and start from this point on and do it on my other computer, which unfortunately the acoustics is not very good. But let me show you. Here, you say finish. There we are. It crashed. Okay, so I go and repeat all this stuff on my other computer up to this point, and then I'm going to come back and later on create two video clips. One of them is good acoustics, the one that I just showed you. The other one is a terrible acoustics. The second part, and I'm going to join them together. Hopefully, it's going to come out to be something respectable. We'll see. I don't know. So this is the second part of the video on my other laptops. This is where it crashed, exactly the location where it crashed when I tried to generate 2D plot, okay? So I redid this thing. Hopefully the sound is going to come out to be okay here, but we'll find out. So you put the cursor there, right click, 2D display, and then you say next, one graph. And when I said finish in the first part of the video on my other laptop, it crashed. But here, it won't crash. And it says, okay, where do you want to actually, monitor the results? So I'm going to minimize this. And notice that in the background, you can go and select the different nodes. Okay, these are the different nodes. And the one that I want is, I think the one, it's exactly in the middle. If you know what it is, then you can get it. Otherwise, there are other ways of doing it. So for example, I think this is in the middle. Maybe node number 8, I don't know. I say add. Okay, and then I say close. So that plot that is actually hiding back there, let me bring that plot for you. Move this thing out of the way here. Restore. This is the plot. Okay. Now let's get these things out of the way. A couple of things that I need to show you. Get these things out of the way. Now, if you put the cursor on this axis. Right click and say options. Just wait. There are certain things you can do here. So let me actually go ahead. This is, if you put the cursor this time, let me put it on. Let me put it on this curve here. Right click options. What I'm going to do is there are different options that you can bring in. None of them is what I want actually. So right now, let's set the scale. Right click options. Yeah, cancel. Sorry. Put the cursor on the white area. Options. Aha, right there. So I don't want the MKS unit. I want to use the option, the units that are used in my problem. Namely, there were inches and pounds, etc. Notice that, first of all, I say, okay, this meter, see, these are going to change to inches. The second thing is that these are amplitude. I don't want amplitude. And I think you have to do it here. Just 1 second. Let's see now. There's a place that you can set. No, it's not there. I keep forgetting that. Right click, options. Put the cursor on this, right click, options. Oh, you know what? I'm sorry. Put the cursor right there, right click, format. Format, not options. Okay. If you put it here, obviously you don't get format. Okay. If you put it on the curve, you don't get format. But if you put it on this, the legend here, right click, format, we wanted not the amplitude, we wanted real value, positive and negative. And there we are. You can see that. So this is supposed to be that sinusoid that I showed you in my MathCAD spreadsheet when I did them. Now the values are very close also. It's kind of hard to see. The values are close. So yeah, I think in the plot that I showed you, it was 0.005 or something like that. Now, one other thing, when you're done here, let me minimize this. If you go to damping, right there, damping, you click on the wrench, notice that automatically a 1% damping is taken for all the modes, okay? So let me make it undamped, okay? Undamp, say undamp, say okay, and say okay. Now, if you double click on that plot again right there, you don't have to run anything because this is all already, that's the whole idea behind modal damping. See, basically there is no change because what we're getting is the steady state response. This transient dynamics that you're getting out of Catia or is called the steady state response. If it's the steady state, damping will not have an effect. Damping will have absolutely no effect if we're looking at the steady well, I really should not say it does not. It does have an effect on the amplitude. Okay, it does have an effect on the amplitude, but not on the. There's going to wiggle. You're not going to get transient responses here. Okay, yeah. So it will have an effect on amplitude. Just to convince you. So let's cancel that and close that. Let's go to the damping and make it a lot bigger. So damping, let's make it 10%. 10%. How about making it really pronounced, maybe 25%? That's a huge 25%. Say okay. We say okay. Now you double click on that. You see, the amplitude actually, is, well, let me run this thing and see what happens, whether there's any difference there. Let me try that. Right click, generate 2D plot. Next. finish. I go and it was number 8, right? Number 8. Can I do that? No, I guess you have to go and select it. It was number 8. This is this. Yeah. Add. You say close the plot. There, right there. You see that? 0.0013. Actually, I'm pretty sure I did not have to run it. It's just that I kept clicking on this plot. This was the old plot based on the damping that I had. Uh, and look, if you double click on this thing, you get the original plot that you got with 0.0048 amplitude, right there. Okay. If you close this and you click on the other guy, that's going to be severely damped, response, which was, let's see, let's change the style here. That right click, format, real, 0.00, about 10 times smaller. So damping does have an effect. It changes the amplitude, but it's still going to be sinusoidal. Okay. Good. So a couple of things that I did, I kind of took me a while to get there, is just use the format to get whether the amplitude you want, whether you want the magnitude, or whether you want the positive and negative variation, etc. And the second thing is that, all right, let's see for a second. Just to convince you that we did not have to run. Let me go and double click on damping. And for damping, let's put down, how about 75? That's gigantic damping. Say OK. And I'm not going to run it. So I put the cursor there, right click, generate 2D display. Next, finish. It says go pick your node, and the node is number 8, I believe. Not that one. Let's go to the left. Oh, here. It's 9. This is 8. There we are. Add. And we say OK. Let's look at our plot right there. It's even smaller. Remember, it was 0.0013. Now it's 0.001 something. Okay, so let me see for a second. Right click, format, real. Right. This was with the damping of can't remember. There's 3 of them. This one was with the current value of damping, which was 75%. Okay. Yeah. Good. That's fine. So in the next video, I'm going to repeat this problem with 3-dimensional elements. You can do it with solid element, you can do it with shell element. You just have to make sure that there is a point there that you can apply the load to that node, or that point here. I showed you what to do. In the case of 3D solid or shell, you have to do a little bit of other work, extra work. So this is fine. And again, you have to do it in two videos. Part 1 with good sound. Part 2, who knows how this is going to come out. Good luck.